Thanks Concawe for having us here and present the work on our NO2 source apportionment viewer. So going back to the previous presentation, which mainly focuses on PM2.5, I would like to add here a few more elements which are relevant for NO2. And this will be a dual presentation, so I will give a short introduction, and then afterwards my colleague Bart Degraeuwe will give a live demonstration of the viewer that we have developed. So I will start with the context and motivation, briefly describing the methodology, and then I will hand over to Bart. So very quickly, the context, which I assume is clear for most of you, but okay, as you know, recently the WHO have updated the air quality guidelines, and especially for NO2, the ambition level has significantly been increased, and target values or guideline values have been reduced from 40 down to 10 micrograms cube for the annual average concentration level. So that is posing significant challenges again to the air quality plant that we will have to design in the future. And as we speak, and Philippe also referred to that already, the Europe is currently revising the air quality directive and is discussing how and at what speeds the European limit values have to be aligned with the WHO guidelines. So that is a bit the context we're working in. The motivation for source apportionment, I think it was already clearly explained by the previous speaker, so I will not spend too much time here. I think source apportionment, as demonstrated before, is really a key element. It's really a key element in the air quality assessment process, and also the starting point for the design of effective air quality plans. Mainly when we do this source apportionment at European scale, rather coarse modeling tools or modeling tools with a coarse grid resolution are used. Typically what also Enrico presented works at a 7 by 7 kilometer resolution. However, we know that when we go to NO2 as a pollutant, which is dominated by traffic, we know that this pollution concentration profiles express very steep gradients, and this was made clear, for example, in a study that we conducted by now 10 years ago, when we have conducted a long-term measurement campaign for a full year around a highway here in Belgium, where we measure that at different locations perpendicular to a highway, and where you can see that the NO2 concentration profile expresses very steep gradients in the vicinity of the highway. And so the black line is giving the concentration level in the background, and the red line and the dots represent the concentration close to the highway, what was observed in the atmosphere. And so this is posing us quite some challenges. How can we combine indeed the European scale, where we see regional hotspots, and combine that with this very fine scale, very granular hotspots related to individual traffic sources. So the objective of this viewer was indeed to develop an online viewer to assess this source apportionment, especially for NO2, applicable for the whole of Europe. And so there is now a focus on two different levels. First of all, we target the roughly 3,000 individual monitoring stations that are available and are available in Europe. And we also made an analysis for roughly 1,000 European cities. And so apart from the source apportionment itself, the viewer also was designed in order to offer an analysis of impact of certain measures. For example, what is the impact of an urban access regulation like low emission zones, for example? What is the impact of changes in activity levels? For example, if you have a modal shift or if there is a road pricing implemented in a certain area. And also upon a specific request, which was also relevant during the last couple of months, the introduction of a new Euro 7 standard and how that is impacting then the NO2 levels over Europe. So that were the objectives. The methodology when we were developing this, we were faced the challenge that I already, I think, presented before. So how can we combine both the long-range transport, which is relevant when we work at European scales and which is relevant anyway also for NO2, and then combine that with the strong gradients close to roads, which have to be tackled at a much higher resolution. And so for the long-range transport part, we rely on chemistry transport models, as was already presented by Enrico. In this particular case, we made use actually of the Sherpa tool that was developed at the GRC and which is available for this type of purposes as well. And what we did, we used this Sherpa for each of these cities to assess the impact or the contribution from the sectors inside the city and outside the city, a bit similar to what Enrico and Philippe already presented before, in order to assess, okay, what is really a local contribution and what is coming from further away. But then on top of that, especially to tackle the impact of individual roads, we have to go to higher resolutions. Therefore, typically we use Gaussian plume models, but also in this context, these are too slow, especially if you want to do it at a European level. So therefore, we developed a bit along the same lines as Sherpa did to mimic a bit the behavior of a chemistry transport model. We developed a quark model, which is also a meta model or a kernel model, as we said, to mimic the physics in the Gaussian dispersion process or in the local dispersion process. And this gives us then concentration levels, annual average concentration levels at a resolution of 100 meters. For the whole of Europe. Then I will not go into details here, but of course you have to combine these different bits and pieces. So we have the long-range transport for the 9 non-traffic sectors for each of the cities. For the traffic part, we have the contribution from inside and outside the city. And then the local traffic is further detailed down to 42 different vehicle types, accounting for different fuel types, different engine categories. And this all is then combined, taking into account proper double counting corrections that we are sure we're not double counting emissions at the different levels. The combination is done at the level of NOx, because that's the most stable indicator to do this kind of combination. And then afterwards, it's converted into an NO2 map, where you see an example here for Graz. So this is a map of Europe at the coarse resolution, but then by combining this quark high resolution component, you obtain typically a map at as I said, at 100 meter resolution, giving you much more detailed information, especially in the urban environments where NO2 is dominated by the traffic sources. So far, so good. So of course, this methodology comes with some strengths, but also weaknesses. So I think the strengths are that by relying on these meta models, as I can say, Sherpa and Quark, we have a fast and user-friendly interface. We are now available to assess the impact of the 10 different sectors that can be assessed separately, both the long range as well as the local traffic impact is taken into account, which is relevant for NO2. I think for PM2.5, as discussed before, it's maybe not that relevant, but for NO2, if you want to do it properly, you have to go down to these high resolutions. And so now the results are available at more than 3,000 individual stations, which are made available by the Environment Agency, and also for roughly 1,000 or 947 European cities we have individual analysis. Obviously, when you develop this type of modeling systems, they also come with caveats or certain weaknesses. I think first of all, it's important to realize that, okay, we don't have a very detailed understanding of the traffic all over Europe. So the analysis here is not based on actual observations or detailed traffic models for the whole of Europe. So it's based on what we call proxy information, which is based on road type and population. So that is still, I would say, a weakness in the methodology, but I think it's a weakness in any methodology that works at European scale, that we still lack a very good and detailed understanding of traffic intensities EU-wide. And then another shortcoming or caveat which is not there yet is the contribution of street canyons. We know that especially for NO2, street canyon increments can be significant. But it's, at the time being, it's impossible to model every street canyon in Europe, so that should be taken into account. This might affect mainly the traffic stations, especially when they are located in street canyon environments, so there might be a mismatch between the model output and what is observed in reality. This is somehow solved with a bias correction, but okay, probably there is room for improvement there. So now I will hand over the floor to my colleague Bart Degraeuwe, who will give you a live demonstration of the viewer to give you some further feeling about what it is about.
Good morning, people in the room and at home. I will give you a quick live demo about the tool that Stijn just introduced. When you open this website, you see this map of Europe with 3,136 station locations, to be precise. And the color scale indicates the concentration in these stations. On the right, you see a quick overview of how the concentrations are distributed. And that allows to check the compliance with different air quality limits, like the current 40 or 20 or 10, the ambitions for the future in terms of NO2 concentrations. As a default, you see here on the upper left, the baseline Clean Air Outlook 2 scenario. You can choose a year. So here you can choose different scenarios from EASA's Clean Air Outlook 2. You can also activate or deactivate several sectors. There are 10 sectors you can switch on or off. Then you can also choose a year for each scenario. Some scenarios go up to 2050. And here, that I will explain later, you can also configure your own Euro 7. We assume Euro 7 would be introduced in 2027, and you can define emission reductions with respect to the current Euro 6 or Euro 6D regulation for passenger cars, petrol and diesel separately, light-duty vehicles, petrol and diesel separately, and heavy-duty trucks. This I will demonstrate later. We applied a combination of Sherpa and Quark and the kernel method to have a very responsive tool, and that I will demonstrate now. So for example, we can quickly go to a future year, for example 2025, and then concentrations are calculated. And if, for example, you're interested in only the contribution of the public power generation and the industry, you can just switch off all the other sectors, save, and then you get a result for only these sectors. So now you have an overview all over Europe, and you see that, for example, in the German Ruhr area and also in southern Poland, these sectors are the main, or also here Po Valley, these sectors are the main contributors to the NO2. We can do the same, for example, for shipping and aviation, and as can be expected, for example, cities with big airports, and there you see Paris, you have slightly lighter blue, so higher concentrations. So of course, this is only the concentration due to aviation and shipping. And so also the big harbors like Antwerp and Rotterdam, they pop out. Then we can go to a specific country. For example, let's select Germany. Then the focus of the tool goes to Germany. I'm going to switch on all the sectors again and recalculate. Save. Then something very interesting you see here is this bar plot. It gives a source apportionment of the contributions of all the sectors. You see that in 2025, power sector is the most important, and then on second place come industry and traffic. If we go back to 2015, we see a very different picture. Back in 2015, or more years ago, traffic was really the dominant contributor to NOx emissions and NO2 concentrations. But due to the Euro 6 for trucks and the Euro 6D that was introduced after Dieselgate, the concentration and the emissions of NOx of transport went down significantly, and that made that the relative importance of traffic is declining, and other sectors are a bit taking over. Let's introduce now a Euro 7 scenario. I can do that here. Of course, we have to go to a year, for example, in the future. And if we introduce Euro 7 in 2027, for example, we go now to 2035, when this Euro 7 has already in place for 8 years. And this we can do in this menu. As an example, I could take the impact assessment that was done for Euro 7, and I chose here the policy option 3, so the most ambitious policy option. It would mean a reduction of 54% for petrol cars, even about 90% for diesel cars. Also for light duty, it would be 50, and here about 90, and also for the trucks, a reduction of about 90%. We save these reductions, and immediately, not here on my laptop, but somewhere a server at VITO calculates the concentrations for all the air quality stations in Europe. We see that if reaching 10 micrograms or even 20 micrograms would be the ambition, there are still many points that are yellow, above 10 or even above 20 micrograms. So also local measures are needed to achieve 20 or 10 micrograms in the future. So then we go to the city scenarios tab, and we can zoom in on a city. Let's take Cologne, for example. There are, as Stijn already mentioned, 948 cities that you can select. After having selected a city, you see here a source apportionment. This is very similar to the source apportionment shown by Enrico and Philippe in the Atlas. This case is for Cologne. We can now press Start Calculation, and we get a concentration map for Cologne. This map is not telling much because the color scale is not appropriate here, and because we're in 2035, default of 40 is a bit high, and so we can go maybe to 15, and then we see a bit more contrast in this map, and we see still the roads coming out. Okay. If we still want to go to, one thing I forgot, we can also select this as a difference map with the base case scenario, so without the Euro 7. Then we calculate this and we get a difference map. Also here we have to adjust the scale a little bit. If we adjust this to 1 microgram, we see that, of course, a regulation on traffic, Euro 7 has the biggest impact on the major roads and also on big roads in the city, and you see bigger reductions than typically outside the city. And then the last option that I want to show you is this urban access module. So here you can change for 42 vehicle types grouped into passenger cars, light duty vehicles, two-wheelers, heavy duty and buses. For all these vehicle types, you can, for the fuel and Euro norm, switch them on or off. So I could, for example, by checking out this box, ban all the diesel passenger cars in Cologne. Or I could also, for example, if I leave them on, I can, at the fuel level or at the Euro norm level, also change the activity. I could make a very specific scenario, for example, with a road pricing scenario. If I assume, okay, these tariffs will reduce to lead to a 90% reduction, a 10% reduction of the traffic, I can introduce here activity changes, for example, and so I can introduce a reduction of 10%, for example, and this reduction is then applied to all the lower levels. I will, for example, apply a diesel ban, and also for light duty vehicles, I will switch them off. I save this, and then I press again the calculation button, and I get another difference map for this, for Cologne. And then there are some other analytics we have here. So you have here a detail of the fleet composition and the NOx emissions, so the vehicle kilometers traveled and the NOx emissions of each corresponding vehicle type. And then here for the base case and for the scenario. Also, you get some concentration overview statistics. So for the base case and the scenario, you see the reductions of the concentrations averaged all over the city, and the contributions from traffic inside and outside the city. All over the city, this might seem a limited effect, 0.3 micrograms, but taking into account that the ambition is to reach 10 micrograms, and this is still a significant reduction. And of course, around bigger roads, the impacts are much bigger. You can check here on the scale, and they're above 1 microgram, so more than 10% of the limit value. So these are the most important functions of this tool. It's all nice, you see, very responsive. You can quickly get an idea of what the impact of different measures is, what the impact of different sectors is on the NO2 concentration in 1,000 cities in Europe. You can scroll from future years to past years. If we quickly go back and we calculate, we see that in the past, a similar reduction would have a much bigger effect. That's because of the relative importance of traffic that reduced over the years. But as Stijn also mentioned, there are some caveats. For example, the traffic data set is a generic data set for the whole of Europe. It's unfeasible to go to every city in Europe and collect the most accurate traffic data. That would be really a huge effort. And also street canyons are not included. So you see the streets here popping out, but that's the effect just of the traffic. But if there are also high buildings around these streets, that can easily double the concentrations in some cases. A narrow street with a lot of traffic and high buildings around, like some big canyons here in Brussels, can easily double the concentration. That effect is not taken into account here. So while you're playing around with this tool, I would also ask you also to read the manual to correctly interpret the results. Thank you very much for your attention.